Good evening, everyone. Today I'm very happy to introduce my colleague Jeremiah Blocky. Jeremiah is a theoretical computer scientist who is interested in applying fundamental ideas from computer science to address practical problems in usable privacy and security. Jeremiah's research interests span several topics. For example, developing usable authentication protocols for humans, exploring easy ways for humans to create and remember multiple strong passwords, and designing secure cryptographic protocols that are so simple that they can be run by humans. Prior to joining our department, Jeremiah did his PhD from CMU and was also a postdoc at Microsoft Research New England. Today, Jeremiah will be talking about usable and secure human authentication.
All right. Thanks for the introduction. So I'm going to talk to you today about creating and remembering multiple passwords. So this talk is on a collection of works with some of my co-authors. I've been fortunate to have the opportunity to work with a lot of great people over the years. So shown up here on the slide, we have my advisors, Manuel Blum and Anupam Datta, and Saranga Komanduri, who was a grad student with me at Carnegie Mellon, and his advisor, Lori Craner. So to start off this talk, I want to ask you to memorize a few secrets. So I want you to imagine that Bill Clinton is standing on this beach here, and I want you to imagine that he is tickling a peach. All right, take a second and really visualize that. Maybe the peach is laughing as Bill Clinton's tickling it. There will be a test at the end of the talk. All right, so that's person, action, object. Bill Clinton tickling a peach. All right, everyone got it? Let's move on to our second experiment. Let's imagine Albert Einstein standing in this, on this railroad track, and I want you to imagine that he's puckering up and kissing a piranha. All right, everyone got it? That's Albert Einstein kissing a piranha. Really try to visualize that. Okay, so today we're going to be talking about password management, and password management is the task that we all face every day when we go online, visit a website, and that website requires us to either create a password or remember a password that we've already created to authenticate. The challenge is that users don't just have one password, they have multiple accounts that they need to authenticate with. They need to create and remember passwords for all of these different accounts. So there's two competing goals when the user tries to manage his passwords, security and usability. And informally, security means that we don't want adversaries cracking into our accounts, stealing our money. Usability means that we don't want to tear our hair out trying to remember all of these darn passwords. So let's look first at the issue of security. What could go wrong? And in increasing order of danger, there are three types of attacks that an adversary could mount: online attacks, offline attacks, and plaintext recovery attacks. I'll illustrate each attack in the next few slides. So your online attack is your simplest form of attack. Here the user registers an account, picks his favorite password. Maybe this is a bank account and he puts a bunch of money in his bank account. And now the adversary just comes along and he tries lots of popular password guesses. So maybe he tries password, he doesn't get in. He tries 1, 2, 3, 4, 5, 6. In this case, he gets in and can steal the user's money. So to defend against online attacks, oftentimes organizations institute some sort of K-strikes policy in which the user is locked out after a few incorrect guesses. These policies are relatively effective if the user picks a strong password. But of course, if users select predictable passwords like 1, 2, 3, 4, 5, 6, there's a chance that the adversary might still break in. The second type of attack is even more dangerous. Here, the user registers for an account with his favorite password again, and the server picks a random value called salt, and they append this value to the user's password, in this case unbreakable with the salt value appended, and they run this value through a hash function. And what they store on their server is the cryptographic hash of the password with the salt appended. So what can happen due to vulnerabilities in the software that the server is running or due to configuration errors? oftentimes an adversary is able to break into the server and steal the cryptographic hash file. In this case, the adversary can try as many guesses as he wants. He's only limited by the resources that he's willing to invest trying to crack the user's password. So, here the adversary might download his favorite tool. There's, lots of open source tools that the adversary could use. John the Ripper is one of them. He can rent time on Amazon's cloud, or he can use his own computer, and he can just brute force, try lots and lots of guesses in a large dictionary and see if the user's password matches any of these passwords. So this is unfortunately a common problem. Password breaches at major companies have affected millions of users. And as I've given this talk over the year, this wall of shame, if you will, has grown and grown and grown. So here's my slide from 4 or 5 years ago. Here's a more recent version of the slide, and Yahoo really gets extra credit for releasing the cryptographic hash values of 500 million users. This was in the news a week and a half ago, I think, where it was 500 billion password hashes, and they've been leaked. So if you have an account on Yahoo, an adversary potentially is running this type of attack right now against your very own password. All right, so the final type of attack is a plaintext recovery attack. And phishing is one example of a plaintext recovery attack. So in this case, the user thinks he's logging into paypal.com, but whoops, he didn't check the URL carefully enough. This is actually paypal.com. And in this case, he just sends the adversary the password directly. Notice that in this case, it doesn't really matter how strong the user's password is, because he just gave it to the adversary. There's no need for the adversary to crack the password, he just has it. So phishing is one example of this type of attack. Of course, there are lots of other examples. You could have malware on your computer, you could have a hidden camera when you log in, or the website where you have the account may just not encrypt their passwords, period. For example, RockU developed games for Facebook, and they decided not to encrypt their passwords. And later, someone was able to break into their servers using an basic SQL injection attack. And there were 32.6 million passwords that are now published online because of this. And plaintext recovery is a real issue. It not only affects the account that was breached, but it can affect other accounts as well. So in particular, users often reuse the same password at multiple accounts. So if the user obtains your paypal.com password, perhaps he can try using the same password at other accounts and see if he's successful. And the problem propagates. All right, so the user is given the task of creating and remembering multiple different passwords in the face of all these different threats. And this is a challenging problem. And there's lots of advice that we tend to give users traditionally. And the advice typically sounds something like the following. Don't make your password too short. Use a mix of upper and lowercase letters. Use numbers as well as letters. Don't use words or names. Use special symbols. Don't write your password down. Don't ever reuse your passwords. And oh, by the way, if you could change them every 90 days, that would be great. Yeah, question?
Yeah, sorry. There's a program called ePass. Could I please? So there are programs called ePasses that are password management. And last time I counted the accounts that I have with is almost 20, and each one of them is either a different password, and it's really hard to track down all the passwords. Sometimes you forget them. So there are programs called ePass. I'm thinking of actually using one of these programs. So what do you think of that?
Okay, yeah, that's a great question. So there are password managers that kind of automate the task of creating and remembering multiple passwords. And password managers come with trade-offs, security and usability trade-offs. So one password manager called LastPass has kind of been a frequent target recently. There was a breach back in 2015 and a recent security vulnerability in 2016. So, while it addresses some security concerns, there's also a single point of failure. And if you implement the password manager incorrectly, or if you enter your master password on any machine that's infected, then you've just given the adversary all of your credentials. So there are costs and benefits to using a password manager, and you would have to evaluate those costs and benefits. For example, if you tend to authenticate frequently from public computers or from a friend's computer, I would recommend against using a password manager, because now you have to expose your master password on multiple different devices. And if you can't ensure that every of these devices is malware free, then you're exposing your master password every time you authenticate. So that's a great question. Okay, so right, this is a challenging problem, and that leads me to the second point. Users are frustrated with all these suggestions. It's just unusable. You can't follow all of these suggestions. It's impossible. So there's a need to reevaluate traditional advice. And Randall Munroe, author of the popular webcomic XKCD, in fact, suggested that we've been doing passwords wrong for many years. So, typically, if you follow the suggestions, you might pick a word, make some number substitutions, add some special symbols at the end. He's suggesting that these types of passwords have much lower entropy. They're much easier to crack than just picking 4 random words. And he's suggesting that 4 random words are actually much easier to remember than a password that looks like this. Now, there's been some interesting studies recently, actually coming out of Purdue, in which they actually asked users to pick word-based passwords, XKCD style, and they found that when users are providing the source of randomness, actually there's a pretty high collision rate. So with user randomness, these passwords actually aren't that secure. You might think that they have 44 bits of entropy, and that's true if you pick each word independently, uniformly at random. But when users are asked to select these words, it oftentimes isn't independent. Their selections oftentimes aren't at random. All right, so let's look at a couple password management strategies that a user might adopt. So scheme 1 we'll call reuse. And here, just imagine picking 4 random words, XKCD style, and reusing that password at every different account. So at Amazon, your password is correct horse battery staple. At eBay, your password is also correct horse battery staple, etc. All right, well, there's a natural variant of this called strong random independent, which is basically the same thing, except for each different account, you pick a different set of 4 words. So Amazon might be correct horse battery staple, and eBay might be banana, baseball bat, potato, table, or something like that. And for every new website that you create, you just memorize 4 new words. So intuitively, you might think the first one sounds easy to do, and the second one sounds quite challenging. But can we actually quantify this intuition? All right, so let's go back to the problem of password management, and let's look first at usability. How can we actually quantify the usability of a proposed password management strategy? So to talk about usability, we have to talk about human memory. And this is challenging because human memory is not a hard disk, right? This is not just a platter where you can execute read and write operations. Human memory is lossy. That's what makes the problem challenging. And human memory doesn't work by just simply writing to a cell and reading from a cell. Well, what does human memory look like? Human memory is associative. So if I tell you the word apple, you might be reminded of certain products constructed by a company named Apple. That might remind you of text messages you sent on said product, or it might remind you of the late CEO of that company. That might remind you of other famous CEOs, and that might remind you of other operating systems designed by that CEO. Or maybe the word apple will remind you of other fruits. In this case, you might think of oranges, you might think of orange juice, and then you might start thinking about what you had for breakfast. So when we talk about memory, it's in human memory, it's important to think about cues. What was the context when a memory was created and stored in the human brain? The context includes the surrounding environment when a new secret is memorized. That might include sounds, what you're hearing around you. It might include your visual surroundings. Maybe you're sitting at your desk when you're creating a new password. And it might involve the website that you're sitting in front of. Probably just a text box with the label password. Maybe you're also thinking about some other stuff like tests that you have to take later in the week and whatnot. So later on, when you try to retrieve this, this secret, much of this context will be lost. So later when you try to retrieve your password, probably the only context that's the same is just this text box that says Amazon and password. All right, so how can we quantify usability? Well, a first attempt to quantify usability involves chunking. So suppose I ask you to memorize the following string, NBC, CBS, ABC. Probably not too difficult, right? Now suppose I ask you to memorize this string, TKQIZRLWP. Probably a little bit more challenging. Why is that? Well, the first string is 3 chunks of information, 3 popular broadcasting companies that most of us are familiar with. And the second string is 9 chunks of information. Unless you can find some sort of meaningful way to combine these characters into meaningful words, it's 9 independent pieces of information that you have to memorize. So this suggests a natural goal, which is just minimize the number of chunks in all of your passwords. And this is a natural goal, but I want to argue that this is a very incomplete goal. Why do I argue that this is incomplete? Well, because human memory is vast but lossy. We have plenty of space or capacity in our brains to store all of these secrets, but yet our brain continually discards the passwords that we've memorized. We've all experienced this at one time or another. So our basic premise is that if you memorize a secret, you need to rehearse it or you're likely to forget that secret. Now the question is, how much work do you actually have to do to memorize and rehearse all the secrets? And to quantify usability, we're going to introduce a rehearsal assumption, which basically quantifies how often you'll need to rehearse the secret if you want to continue remembering it. So, okay, here in this picture, suppose the user hasn't logged into Amazon for a while, maybe 3 months. In this case, the user is likely to forget that particular password. So our memory capability is motivated by a user study we conducted. And in this user study, we gave users 4 person-action-object stories, much like the ones I gave you at the start of this lecture, and asked them to memorize all 4 of these stories. And each point on this graph represents a point in time at which we asked users to return and rehearse all 4 of their person-action-object stories. And here, this graph shows the fraction of users that were successful when they returned, divided by the total fraction of users that actually returned to complete that rehearsal round. And here we can see that with 10 rehearsals over 156 days, users are highly successful remembering all 4 of their person-action-object stories. In fact, on the last rehearsal, this is the 10th rehearsal, 156 days after they initially memorized all 4 stories, 100% of users that returned remembered all 4 of their stories. This is even after a gap of about 64 days since their previous rehearsal. The key point here is that memories are strengthened with repetition. Yeah?
Do you have any kind of slide showing the number of, like the raw number of returners and such for those?
Oh, raw number of returners. I think it was about 50% of users completed every rehearsal round. This was a study on Amazon Mechanical Turk, and we initially invited everyone to complete the first phase, which was memorization phase. And after they completed it, we would send them emails to ask them to return. And if a user wasn't able to return in a timely fashion, then we had to drop them from the study. If a user returned and forgot one of their stories, then we would remind them and invite them to continue participating. But the key challenge here is actually, you know, a lot of users on Mechanical Turk just don't return for follow-up studies, period. And in fact, you'll see that from the memorization phase to the first rehearsal round, where the drop-off is, you know, about 60% of users returned for that first round. Conditioned on users returning for that first round, the return rate was pretty high. So users that return tend to keep returning, and users that don't like to participate in follow-up studies just don't participate. This is kind of a global phenomena in all studies that you would conduct on Mechanical Turk with a follow-up phase. You know, every study I've seen has a return rate of about 60%. So for whatever reason, you know, 40% of users either miss the reminder or they're too busy when they get it and just never return. Okay, so motivated by the user study and by some other older studies in cognitive psychology, we introduced the following rehearsal assumption. The assumption basically says that you'll remember a secret that you've memorized if you rehearse it at least once during each of the following time intervals. Once between day 1 and day 2, once between day 2 and day 4, once between day 4 and day 8. Of course, you can adjust the parameters of this model so that, you know, the intervals don't double each time. But for simplicity, we're going to just use this as a running example. Okay, so now we have this assumption. Let's suppose now that the user visits their Amazon account maybe on day 4, day 5, day 8. Well, in this case, they're naturally going to satisfy some of these rehearsal requirements. Every time they visit Amazon, they have to type in their password and rehearse the corresponding secret. All right, let's suppose that the user also has a Google account and that he visits Google maybe at day 1.5, maybe day 4.5, maybe day 9, etc. Well, okay, in this case, we can use x sub t to denote the total number of extra rehearsals necessary to remember all of your passwords for t days. So in this case, let's suppose that I ask you for the value of x8. How many extra rehearsals would the user need to do to remember all of his passwords for 8 days? Well, the answer depends on what strategy the user is adopting. Suppose that the user is reusing the same password everywhere. How many extra rehearsals does that user need to do? Anyone want to venture a guess? Yeah?
If the password is the same for all accounts, then there are no extra rehearsals.
Right. Yeah. If the password's the same, then there's no extra rehearsals because you get a practice round during each of these intervals. Suppose instead that the user picks independent passwords for each account. How many extra rehearsals would the user need to do in this case?
Maybe like 1.5, so a half an extra rehearsal kind of thing.
Okay,
So,
well,
like,
so let's, I guess, break this down. The user has an Amazon password, which they don't rehearse during this window. So if we want to guarantee that the user remembers the password, we're going to have to remind the user to rehearse their password once during this window. And that's, you know, an extra rehearsal beyond what they would do in their natural course of internet usage. Similarly, for Google, the user is going to have to be reminded to rehearse his Google password once during this interval because he doesn't visit Google during that time interval. So in this case, there's 2 extra rehearsals that the user would need to do to remember all of his passwords for 8 days. So our usability measure is actually going to be xt, just the total number of extra rehearsals to remember all of your passwords for t days. And now our usability goal is naturally minimize the total number of rehearsal reminders beyond natural internet usage. All right, so we looked at a toy example, but what about users that have, you know, more than 2 accounts? So you can introduce a model of the user. In particular, you can introduce a model of an active user with 75 accounts. You know, some of these accounts they visit every day. Some of the accounts maybe they visit once every week. Maybe some of the accounts they only visit once a month. And now you can actually predict how many extra rehearsals does the user need over his lifetime to remember all of these passwords. And even our active user needs about 3,000 extra rehearsal reminders over his lifetime to remember all of his passwords. If the user reuses the same password, then even our infrequent or occasional user basically never needs an extra rehearsal reminder at all. So our occasional user only needs 0.1. That means with probability 1/10, you might need to send him one rehearsal reminder over his lifetime. And our infrequent user, who's visiting most of his accounts once a month or once a year, think of grandma when you think of the infrequent user, would only need 3 extra rehearsal reminders over his or her lifetime to remember all of her passwords. All right, so we have one scheme that's usable and one scheme that's unusable. So if we weren't concerned about security at all, the answer is obvious. Just reuse the same password. All right, of course, security is an issue. So we have to talk about security and how we want to quantify security. So before I define security formally, let me just go over our high-level approach, our philosophy. So we want to make a dangerous world assumption. A lot of times when people do password analysis, they're only looking at current adversaries. They're looking at how secure their scheme would be against current attackers. But in our view, it's not enough to just defend against existing adversaries, because after you propose a new strategy, the adversary can adapt his scheme to be as effective as possible against your strategy. So we want to make a dangerous world assumption. We want to assume that the adversary is going to adapt his attack to be as effective as possible against our scheme. And we want to provide guarantees even when things go wrong. So this means that even if the adversary sees the cryptographic hash of your password and maybe one of your other passwords, he still shouldn't be able to crack that cryptographic hash. So this means that offline attacks should fail with high probability, and we want to limit the damage of successful phishing attacks. All right, so formally we're going to treat security as a game between the user and the adversary. And the user moves first in this game. He picks his password management strategy, and now he registers at lots of different accounts with passwords following whatever strategy he picked. And now the adversary gets to move. And the adversary gets to point at, let's say one of the user's accounts, in this case PayPal, and say, show me the user's paypal.com password. And in the game, the adversary is shown the user's paypal.com password. Then the adversary gets to point at one of the user's accounts and say, show me the cryptographic hash of the user's, let's say, PlayStation.com password. And in this case, the adversary gets the cryptographic hash value. And now the adversary is given a budget with which to crack the user's password. For example, maybe the adversary is given $1 million to rent computing resources on Amazon Cloud, and now he can use these resources to try to crack the user's password. So he's given a fixed number of guesses that he's able to try, and the specific number of guesses depends largely on the particular password hash function that was used. So if say SHA-256 was your password hash function, then within a second on a GPU, you can evaluate billions and billions of password guesses. If you do a little bit of key stretching, for example, bcrypt, instead of returning the hash value, it iterates this hash function lots of times to make this process more expensive. And there are even more effective key stretching tools besides bcrypt. For example, I might recommend scrypt or other memory hard functions if you want to do password hashing. But once this password hash function is fixed, then there's a cost associated with computing this hash function, and that gives the adversary a fixed number of guesses that he can try. So the user wins this game if the adversary fails to crack any of the passwords that he doesn't already have. So in this case, if the adversary manages to guess any of the user's other passwords other than paypal.com, the adversary would win this game. And if the adversary fails, then the user wins this game. So to formalize this, we say that the adversary can compromise at most R sites, plaintext recovery attacks. And the adversary can execute offline attacks against at most H additional sites. And due to resource constraints, the adversary has a budget Q that he's able to spend during an offline attack. The adversary wins this game if he can compromise any new sites. And this looks like alphabet soup, but throwing all the parameters of the game on one slide, we say that a scheme is Q delta M S R H secure if the probability that the adversary wins this game, given all the parameters, is at most delta. Here, Q is the number of offline guesses, M is the number of user accounts, S is the number of online guesses that the adversary can try before he gets locked out, R is the number of plaintext passwords that the adversary gets to observe, and H is the number of password hashes that the adversary gets to observe. So as a simple example, Q delta M311 security is when the adversary gets one password and one password hash value, and Q guesses to break that password hash, and it's secure if the user wins this game with high probability. All right, well, so what about security? We can use our two toy schemes, again, reusing the same password. We can look at different security parameters. Well, in this case, it's very easy to analyze. Once the adversary gets one password, it's game over. So the scheme isn't secure with R equals 1, it isn't secure with R equals 2, R equals 3, etc. Once the adversary gets one password, it's game over. Similarly, if we pick independent passwords, it doesn't matter how many passwords the adversary actually observes. He's not going to learn anything about the user's other passwords because they're independent. And because they're strong and random, he's unlikely to crack any of these passwords in an offline attack. So in this case, we're secure under all of these attack scenarios. So great, we have one scheme that's usable and highly insecure, another scheme that's highly unusable but secure. The question is, can we find anything better? So our approach, as I hinted at the beginning of the talk, uses person-action-object stories. And we're going to divide these stories into two pieces, a public queue and a private secret. So the public queue is a scene and a person, in this case, LeBron James on the bridge. And the private secret is a random action and a random object that the user has associated with these images. So in this case, LeBron James is kicking a penguin on the bridge. By the way, I don't have a violent imagination. That actually was the randomly generated example. Okay, so once the user has memorized all these stories, what does the login screen look like? Well, the login screen is just a sequence of challenges. In this case, you're asked for the action involving LeBron James on the bridge, then the object, then maybe the object involving Albert Einstein at the railroad tracks. And the user has to type in all of these secrets, or maybe the first 3 letters from each word. All right, and similarly, when the user logs into PayPal, he'll see a similar set of challenges. All right, and if you're paying attention, you'll notice that this first piece of the challenge was the same for PayPal and for eBay, or was that eBay? Sorry, PayPal and Amazon. All right, so we are sharing some of these queues across different websites. And as we saw before, sharing queues has certain usability advantages. One, potentially there's fewer stories to remember overall, and there's also more natural rehearsal for each of the stories that you have to memorize. Now, of course, the question is, what about security? Isn't reusing secrets across websites an insecure practice? Well, no, and we'll use a combinatorial design to ensure that any pair of accounts has at most gamma secret stories in common. So in this case, you might think of gamma as 1, meaning that any pair of accounts that the user has should share at most one common secret. So formally, we can introduce an NL gamma sharing set family, where set family is just a sequence of subsets, S1 through N, Sm. Each of these subsets is a subset of the universe 1 through N. and each subset should have size L. So here, M is the total number of passwords. Each subset corresponds to the secrets that the user might use at a particular account. For example, SI is the secrets that you use to authenticate to account I. And gamma tells you how much information one password might leak about another password. L tells you how long each password is. And N is the total number of secrets that the user has to memorize. This is an NL gamma sharing set family. How many passwords can you actually form if you use this trick? Well, suppose that you only are willing to memorize 4 person action object stories, like the users in our Mechanical Turk study. Well, in this case, I claim that you can actually form up to 14 different passwords with the guarantee that every password uses 4 secrets and any pair of passwords intersects in at most 2 secrets. So in this case, you have security against an adversary who sees one of your passwords, but you don't provide security against an adversary who sees 2 of your passwords. After an adversary sees 2 of your passwords, he can potentially start to predict other passwords. All right, well, suppose, an adversary with 1 password is unlikely to guess any of your other passwords. Suppose that you have more than 14 accounts. Suppose that you have 75 accounts. Well, in this case, if you're willing to memorize 7 person action object stories, you can generate up to 75 passwords with the same exact security guarantee. All right, that's great, but what if you want stronger security guarantees? Well, okay, suppose that you're willing to memorize 15 person action object stories. In this case, you can have 75 unique passwords with security against any adversary who's seen up to 2 of your passwords. So if the adversary gets to see any 2 of your passwords of his choosing, he still can't predict any of your other passwords. And if you're really motivated, you could memorize 43 person action object stories. And in this case, you'd get a very extreme security guarantee. Any adversary who's seen up to 6 of your passwords is still not going to be able to predict any of your other passwords. Yeah.
If you do 4 person action object stories, do you know
Yeah.
how many passwords you could do with, say, the 2 password security?
Oh, if you memorize 4 person action object stories, with security against 2. Off the top of my head, I don't know. My guess is not very many, but I'd have to actually try to run a computer program to compute the corresponding combinatorial design. My intuition is not very many, but I could be wrong. I could be wrong about that. So yeah, to get stronger guarantees, this technique is particularly powerful as the number of stories grows. With 15 stories, I can get security 2 and 75 accounts. If I just add 1 more story, I think the number of passwords that I could form skyrockets up to like 160 or something like that. The technique is powerful, and you do get a lot of growth once you pass a certain threshold. But my conjecture is that if you want security 2 with 4 stories, you're still not going to be past that threshold, and the construction's not going to be particularly large. So my guess is you can't create too many passwords. Yeah.
I was wondering who gets to choose the verb.
Use your mic, please.
Oh.
I was wondering who gets to choose the action and the object.
Yeah, that's an excellent question. So we're recommending that these are actually random system-assigned actions and objects. In the user study we conducted, these were system-assigned actions and objects that the users were memorizing. And the reason we use system-assigned actions and objects is that if users are selecting their own actions and objects, they might select an action or an object that's highly correlated with the person or scene that they see. So if they have Bill Clinton on the beach, for example, maybe actions like swimming or objects like shark are natural objects to associate with a beach. But in our case, it was tickling a peach. because these are random actions and objects, it's not something that's necessarily associated with the person or scene. And in fact, what we found is that these random system-assigned actions and objects are memorable. So if you can go with system-assigned words, that's certainly the most secure option. Yeah.
So, I wanted to ask, the challenge posed by Amazon is fixed over
Yes.
time.
Yes.
And do Amazon and PayPal need to coordinate what challenges they will be posing?
Right. Okay, that's an excellent question. Yes. First of all, the challenge that you would see when you visit Amazon is going to be fixed. It's going to be the same every time. So your password is going to be the same every time you visit Amazon. Do Amazon and eBay need to coordinate? I would love it if they would. Realistically, I don't think this is ever going to happen. So the way I use the scheme personally is I just have a spreadsheet on Google where I record Amazon and the associated queues. We are working on developing a browser extension which functions like a password manager, except that it doesn't keep any secret state. It just stores the challenges that you would need to authenticate to every different website.
And sorry. And one more question, in this one, so suppose today a kid starts and he's able to remember only 4 stories and 14 passwords suffices.
Yeah.
As he grows old, he might be willing to learn more stories.
Yeah.
And does your combinatorial design update dynamically, or does it need to be refreshed completely?
That's a great question. So currently, no, the combinatorial design does not update dynamically. Getting a combinatorial design that does update dynamically is one of the research directions that where we're trying to push hard right now. So that is a great question, and I think the intuition is spot on. It's going to be tough for a user to memorize 15 stories all at once, and in fact, we would recommend if you adopt the scheme as is, that you kind of memorize the stories in advance before you start using the scheme, and you just slowly memorize the stories. Eventually, you've memorized enough stories, and now you can start using the scheme. So that's a great question, and the intuition is spot on. We are trying very hard to push in that direction and kind of allow for incremental memorization, so a user can start using the scheme after they memorize 4 stories, but increase security over time. All right, so as far as security goes, if you use this 36-2 sharing set family, so memorizing 15 stories, each story gives you 2 secrets, an action, and an object, then you can get security under the first 3 attack scenarios. But if the adversary sees 2 of your passwords, then potentially when he sees another password, he knows 4 of the secrets, and he can brute force over the remaining 2 secrets. So it's not secure if the adversary sees any 2 passwords of his choosing and then gets to execute an offline attack. And if you only memorize 4 stories or 7 stories, you pick this weaker version, then you provide security under this first scenario where the adversary gets to see any one of your passwords. But security starts to break down if the adversary gets more information. For example, if he sees one of your passwords and then gets the cryptographic hash, then he can execute a successful offline attack. All right, so as far as usability, we can run the same algorithm to predict how many extra rehearsals the user would need over his lifetime to remember these secrets. And here we can see that our active user is going to need somewhere between 4 and 10 extra rehearsals over his lifetime to remember all of these secrets. And in fact, most of these rehearsals are going to come within the first week after memorizing all the secrets. So after, in the first week, you might have to annoy the user a few times, but after that first week, most likely the user is going to continue to remember all of the secrets that he's remembered. So now we have schemes that, it's a little bit more difficult to use than just reusing the same password, but much more secure. And it's a little bit less secure than picking strong random independent passwords, but much more usable. All right, so future directions, as we kind of hinted at, how would you actually use this scheme? Well, if you wanted to adopt it right now, you would have to basically set up your own spreadsheet and record Amazon, and here's the associated cues, LeBron James, action, Bill Clinton, object, etc. So we'd like to develop a browser extension, and this is a project that we're working on right now, which would allow you to have the computer just show you the appropriate cues when you log in. So right now for me, the most annoying feature of the scheme is not remembering the secrets, but opening up the spreadsheet and finding the associated cues. If we can eliminate this challenge, I think the scheme is going to be much easier to use. And also, as Hamanta indicated, gradual password strengthening. So can we allow a user to memorize four person action object stories initially and increase security over time instead of demanding that the users memorize all of their secrets up front? Another important direction is recovering forgotten secrets. What happens if the user does happen to forget one of these person action object stories? We have some ideas about ways to construct a secure recovery mechanism, which would allow a user to recover any forgotten secret, given that he can remember most of his other stories. And in this case, the idea would be to use error correcting codes and some other tools from cryptography to make the mechanism something that's completely inaccessible to an adversary who doesn't already know most of the user's secrets. And a final direction, one that I think is potentially interesting to explore, is intrusion detection. So we have a model, space repetition model, that allows us to predict when a user is going to forget their password if they don't rehearse. What happens if you're a server and you observe a user logging in at time 1? He's successful. You observe him log in an hour later. He's successful. And then an hour later, the user logs in 3 times and he's unsuccessful every time. Well, that seems a little bit suspicious because it seems like the user has memorized the password and all of a sudden he's forgotten it. Whereas if you see the user log in once at day 1 and he gets the password correct, and then maybe 3 months later he tries to log in and he's incorrect 3 times, this might be less suspicious. So the question is whether we can use the space repetition model to actually gain some intuition and predict which login attempts may or may not be an intruder trying to access the user's account. So thank you for listening, and I'll take any questions. All right, I think we had one.
Yes.
Yeah.
What is the role of 2FA in the password cracking?
What is the role of two-factor authentication?
Yes, please, yeah.
Two-factor authentication could certainly be used in addition to any of the schemes that we propose. Of course, when two-factor authentication is great, I'd encourage anyone to adopt it whenever possible. It's not universally available. Some companies offer it. Some, Google offers it. Some organizations tend not to offer it. But even if you use two-factor authentication, there's still that risk that an adversary will break into the server and be able to execute that offline attack on your password. So even then, it's even if you're using two-factor authentication, it's still good to have independent passwords if possible. Any other questions? Yeah.
I think I already asked you. If that password-based authentication scheme has such difficulties, why don't we move to hardware-based authentication or fingerprint?
Okay, this is a great question. There's been a lot of work over really the last few decades trying to replace passwords. So you have hardware authentication, you have biometrics, you have graphical passwords, you have your RSA, secure ID tokens. And in 2004, Bill Gates kind of famously declared the password is dead. But here's a plot of the number of passwords that are being used over time, and this is the point in time at which Bill Gates declares the password is dead, and this is what's happened since. So somehow, despite all of these attempts to replace passwords, they don't seem to be going away. Well, why is that? We have password management software. That's one potential replacement. But as we mentioned earlier, now you have to trust all of the computational devices that you ever use. What happens if one's infected with malware? Or what happens if there's a security breach at one of the password managers? That would be problematic. Of course, password managers are only one alternative. There's like hardware tokens, biometrics, eye scanners. And there was a paper published in 2012 by Bonneau, Hurley, Van Oorschot, and others called The Quest to Replace Passwords. And they kind of looked at all of these proposed replacements and found that really none of them is that silver bullet that we need to replace passwords. So despite all their issues, a password has a low amortized cost per user. So if you're Facebook and you haven't raised capital yet, they had 1 million users before they started to raise any capital. You can't issue all of your customers an RSA secure ID tag. It's just too much money. Passwords are essentially free to implement. They're mature. You have open source implementations of password libraries like bcrypt, so it's kind of free to implement. So if you're Facebook and you have these options, are you going to use passwords, or are you going to use RSA secure ID? Well, of course you're going to use passwords. Similarly, we could think about biometrics. Well, the advantage is there's nothing to remember. I just have to have my finger. But what happens if an adversary is able to obtain my biometric? I can't change my fingerprint. Once it's gone, it's gone. And in fact, I'm kind of leaking my fingerprint every time I touch something. In fact, I'm potentially leaking my fingerprint right now when I wave it in front of the high-definition camera. In fact, a German hacker looked at a high-resolution photo of Angela Merkel, zoomed in on one of her fingers, and actually was able to extract the fingerprint and forge authentication credentials. So there's lots of proposed replacements, but none of these replacements is strictly better than passwords. They have some advantages, but they always come with that critical disadvantage, which means that until we find a replacement that's going to address all of these security and usability criteria, most likely passwords are here to stay, for better or worse.
Any other questions? Yes, thanks.
All right.